So we've defined computable enumerability in this new way, where rather than talk about algorithms which list everything out, which is what the name kind of implies, we instead are talking about uh, 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 this notion of a machine accepting, which is kind of a weakening of the notion of deciding a language, which is what it means to compute. It's kind of a weaker form of computation. So why do we care about this? And is it even different than computability? We still haven't shown. So still haven't found out if R is actually different from Re. We don't know that yet. But what we're going to see immediately in this video is that they are. And so why are they? So we know the halting problem, which I'm going to denote H, is not an R. However, it is obvious. Not obvious enough that you'll know it immediately, but obvious enough that I can explain it extremely quickly, that the halting problem is nonetheless in Re. It is recursively enumerable. Why? Why is the halting problem recursively enumerable? What's an algorithm for it? Remember what the halting problem is. With the halting problem, we were given a machine M. We're given two integers, right? One integer for a machine M. Let's just assume it's the machine, and an input to that machine N. So, given a machine, I'll just say a machine code M, an input N. I'm just going to say given a machine M. Not going to overcomplicate it. Given it a machine M and an input M. I think we're probably comfortable at this point with associating Turing machines with strings, but given a machine M and an input N, simulate M of N. If it ever halts, halt in acceptance. That's it. So we don't know if the machine M is going to halt on an input, but I mean, we could sure as hell try to run it and see what happens, and if it does, say yes, and that is enough to give you a machine that accepts the language. It's a universal Turing machine. This word simulate is something I'm going to use a lot. I just want to remind you, I can say stuff like this because of the existence of a UTM. I'm never using this blue again. UTMs exist, so I can say stuff like this. There exist universal Turing machines. There exist Turing machines that can simulate any other Turing machine. So I can just think about a universal Turing machine that I'm modifying slightly in order to come up with a solution to the halting problem in this way. Or not a solution, but a partial solution. A solution enough to observe that the halting problem is recursively enumerable. So that is that kind of answers this question. The answer is yes, because the halting problem is in here, but not in here. So we have demonstrated the existence of a particular language that is not in one. But the halting problem means more than that. Oh, and by the way, okay, I should probably say this. You know, so finally have this. We have that R. So have that R is not equal to Re. But nonetheless, they're still both countable. They're both still countable, and the reason that they're both still countable is because they both depend on Turing machines existing, right? There's only as many languages in both of these classes as there are Turing machines, and there's a countable number of Turing machines. And so that's why, while these aren't equal, they're still kind of the same size-ish. But that is not the case for this other class I defined before, all, which is just all problems. And these two are not equal to this because this is uncountable. Why? Because all is really, this is literally, too many arrows, this is literally the collection of all infinite bit strings. That's something I should probably also reiterate a bit, is that yes, I do go back and forth between talking about decision problems as if they are sets of strings and as infinite bit strings. I just kind of think of them interchangeably because they are interchangeable. But in a sense, the collection of all problems is literally the collection of all infinite bit strings, and that is very uncountable. And so these are countable sets. This is uncountable. So these are certainly not equal to this. So we have that none of these are equal to each other, these classes I defined before. And we're going to define one more class before the end of this. So that's all well and good. But there's more to say. The halting problem is in some sense the hardest possible problem in Re. It's hard for Re in a certain way. So in a sense, in a very real sense, the halting problem is among the hardest problems in Re, in the following sense. So here's a fact that I think is worth noting about Re. So here's a fact. Here's fact number 3, I guess I'll call it. If, and I know this is not the case, but it's going to be worth noting, if H were in R, then R would equal Re. Then the classes would collapse into each other. So if the halting problem is in, i.e., a computable solution to the halting problem, would imply, could be used essentially. If we had a Turing machine that solved the halting problem, then we could use it to solve every other problem in Re computably. To solve every other problem in Re computably. So this is a way of saying something that I think most people have heard before if they're into computer science. This is a way of saying that H is Re hard. So you've probably heard of things being like NP hard or hard for a particular complexity class. A problem is hard for a class if you could use it to solve every other problem in the class. In whatever way, in whatever resource use or efficiency or whatever is kind of implicitly related to what you're talking about. So, and if a problem is Re hard and also in Re, since additionally H is in Re, we say H is Re complete. So you've probably heard the term NP complete before. The NP is another complexity class. And in some way, NP is actually the same class as Re, except with the word computable replaced with efficiently computable. But that's a whole nother set of videos. But in any case, that's kind of what we're really saying here in a few different ways. So why is that? So here's the proof of that. Suppose there was a Turing machine deciding H. And I know there isn't, but this is still kind of a pattern worth staring at, I think. Suppose there were a Turing machine deciding H. So call it M sub H. Let L just be any problem in Re. So L is just some problem that is recursively enumerable. Let M sub L be the machine accepting M sub H. Or sorry, not accepting M sub H. What am I talking about? The machine accepting L. So what we're going to do is we're going to do this. So consider the following machine. M prime. M prime L is going to be a superpowered version of M sub L. It's going to be an M sub L that does more than just accept. It's going to decide M. So here's what it does. On an input X, simulate M sub H of M sub L comma X. So what does this mean? It means I'm going to simulate the halting problem being used on the machine I have for accepting L being run on X. So right now what I have is a machine that accepts L, right? I have a machine that I can feed an input to, and if it halts, then it's an L. And that's exactly what I'm asking right here. So this tells me, if M sub L halts on X. If it does, then M sub L of X accepts, because that's all it can do. So halt and accept. Otherwise, reject. I don't know why I wrote up in this corner like this, but that's it. So clearly, the machine M sub L prime decides L. So L is decidable, i.e. L is in R. Therefore, R is RE. So what have we shown? We've shown that if L is in Re, then L is in R. And so Re is a subset of R. But also R is a subset of Re. So R equals Re. So if you got two subsets going in the same, if A is a subset of B and B is a subset of A, then A and B are equal. So what have we really done here? It's a super simple proof, but what did we really just say? We basically said that if you have a solution to the halting problem, and if you have a machine that accepts something, that accepts a language, then you could just short circuit that shortcoming, right? The whole problem with accepting as like the whole reason that accepting is weaker than deciding is because we don't know if something's going to halt or not. If we did know that something was going to halt, then we could just check if it halts, and then if it doesn't halt, then stop, then reject, and then we kind of short-circuited the problems with acceptability and just turned them into decidability. If you have a solution to the halting problem, there is no difference between these two concepts. There really isn't. So the halting problem is fundamental. It's sort of it's fundamental to Re. It's like one of the most important classes for understanding Re. It's not just another computably enumerable problem. It is kind of the flagship computably enumerable problem because it is powerful. It's an important enough and powerful enough problem that it can be used to it's sort of defining of the class. If it weren't in the class and hard for the class, if you had a solution to it that's computable, then there wouldn't be any difference between Re and R.